All right, so today, let's put on our detective hats. We're going to dive into a little chemical detective story. Our mission? To unmask these mysterious organic compounds using some pretty classic lab techniques and, a bit of clever deduction. Let's crack this case.
Okay, picture this. A vial of some mystery powder just lands on your desk. What is it? Could be a new medicine, maybe a dangerous pollutant, or who knows what else. It's your job to figure out its identity. But wow, with a million possibilities, where do you even start?
Well, the first step in any good investigation, right? You gotta find out who's at the scene of the crime. In chemistry, that means we need to identify the basic elements that are present in our mystery compound. We're looking for those fundamental building blocks. So, to get our clues, we need a kind of master key. And in this world, that key is called Lasagna's test. See, the problem is, elements in organic compounds are kind of locked together tightly in these covalent bonds, which makes them super hard to detect. This test, though, it's brilliant. It basically unlocks them, converting them into an ionic form that makes them talk to us. Honestly, it's the one step that makes this whole investigation even possible. All right, our first suspect on the list is nitrogen. To see if it's hanging around, we take our unlocked sample, that's the sodium fusion extract, and run it through a pretty specific process. We boil it with some ferrous sulfate, carefully add a bit of acid, and then we just wait for that telltale sign, the clue that's going to confirm our hunch. And boom, there it is, the formation of this vibrant, just unmistakable Prussian blue color. That's our smoking gun. If you see this, you know without a shadow of a doubt that nitrogen is a key player in your mystery substance. Case closed on that suspect. Next. Okay, next up, we're checking for a possible accomplice, sulfur. And our detective kit has two different tools for this one. We can either go the lead acetate route, or we can try the sodium nitroprusside test. So let's see what clues these two different methods give us, shall we? And you know what's really cool here? Two totally different paths lead us to the exact same conclusion. One test gives us the solid black precipitate, while the other produces this absolutely stunning deep violet color. Either one of these is like a clear confession. Sulfur is definitely in the building. But hold on. What if nitrogen and sulfur were actually in on it together? The plot thickens, right? When both of them are present in the same compound, they team up to form something called thiocyanide, and that reacts with iron to give this incredibly dramatic blood red color. It's got to be one of the most striking clues in all of qualitative analysis. Just amazing. And last but not least, we've got to check for the halogen family. We're talking chlorine, bromine, and iodine. The key here is to add some silver nitrate and then see how the stuff that forms, the precipitate, reacts with ammonia. So if you get a white precipitate and it dissolves, that's chlorine. A yellow one that doesn't dissolve at all, that's iodine. See? Each halogen leaves its own unique fingerprint. Okay, so we've identified our suspects. We know who is in the compound. But any good detective knows that's not enough. Now we've got to move to the quantitative phase. We're going to measure exactly how much of each element is actually there. So to figure out the amount of carbon and hydrogen, the absolute backbone of organic chemistry, we use something called Liebig's method. It involves some really careful combustion and measurement. Now, this formula, it might look a little intimidating at first glance, but trust me, it's just a simple calculation to find the percentage of carbon. Let's break it down. See, it's actually pretty straightforward. W is just how much of our mystery substance we started with. Simple. And W1 is the weight of the carbon dioxide gas that gets produced when we burn it. You just plug in those two simple measurements, and bam, you've got a precise percentage. And we can do the exact same thing for those halogens we found earlier. Using what's called the Carius method, we can figure out the precise percentage of, let's say, chlorine in our sample. So the really crucial point here is that we're moving from a simple, yep, it's here, to it's here and it makes up exactly this much of the whole thing.
Now, for nitrogen, we've got two main methods in our arsenal. There's the Dumas method, which is kind of the universal soldier. It works for pretty much any organic compound by collecting pure nitrogen gas. Then there's the Kjeldahl method. It's also super common, but it has a few blind spots. It can't be used for certain types of nitrogen-containing compounds. So you see, choosing the right tool for the job is absolutely key.
All right. Now, before we can write up our final report and officially close this case, there is one absolutely critical step we just can't forget. We have to make sure our evidence is clean.
So why is this so important? Well, think about it. Impurities are like false witnesses in a trial. They can give you totally misleading test results, sending your entire investigation way off course. Getting a pure sample is like securing the crime scene. It makes sure the clues you find are actually reliable.
One of the go-to purification techniques for liquids is distillation. It's all about separating things based on their boiling points. Now, if the boiling points are way different, like with chloroform and aniline, simple distillation works great. But for liquids with really close boiling points, think about crude oil, you need to bring out the big guns, fractional distillation.
And believe me, the purification toolkit is huge. We've got vacuum distillation for those sensitive liquids that would just fall apart with too much heat. There's steam distillation for others like aniline. And for solids, we use this beautiful process called crystallization, which separates a pure solid from all the gunk mixed in with it.
But maybe the most powerful and versatile purification tool of them all is chromatography. I mean, this is a masterful technique that can separate even the most complex, the most stubborn mixtures you can imagine.
The best way to think of it is like a race. You put your mixture at the starting line. That's what we call the stationary phase. Then, the starting gun fires. That's the mobile phase, which is a solvent that washes over everything. Now, because each component in the mixture runs at a different speed, they start to spread out, separating into these pure, distinct bands. It's just such an elegant and incredibly effective way to get a pure sample.
So, let's recap. We've identified the elements, we've measured them, and we've purified our sample. We have totally cracked the case of our mystery compound. But why does any of this really matter outside of the lab? Oh, it matters immensely. These detective skills are literally the foundation for so much of our modern world. They're used to design and purify life-saving drugs. They're used to check our food for harmful pesticides. They help create the new materials for our phones and computers. And yeah, they're even used to solve real-life crimes in forensic science. It's everywhere.
So think about where we started. We had a complete unknown. And through this logical process of deduction, finding clues, measuring the evidence, and purifying the sample, we solved the mystery. We took a simple vial of powder and revealed its complete chemical identity. How cool is that?
You know, this whole process really shows that every substance, every single material has a hidden story to tell. And it kind of makes you wonder, doesn't it? What secrets are hiding in the world all around you right now, just waiting to be unlocked by a little bit of chemistry?